All right, so what I'll talk about is dynamic modalities for social networks. And what I'll present is based on a series of papers, mainly work that I'm doing with Alexandru Balta, who will also be around today later this afternoon, and on papers that we wrote together with students and visitors who were around. So with Zoe Christoph, Jens Ulrich Hansen, Rasmus Rensvig. And the last part of the tutorial will be based on a series of papers that I wrote with Fernando Velasquez Quesada, who is now at the University of Bergen. So what's this tutorial about? I'll use model logics and I apply them to the formal analysis of epistemic social networks. And I organize the tutorial in 3 parts. There will be a part in which I start with the study of belief formation and belief influence in a specific type of social network, and these are sequential social networks. And here I will focus on specific probabilistic epistemic models. I'll explain what these are. And my goal is to model the formation of informational cascades. So that's what I'll do in the first part. Then I'll move on to study social influence in other types of social networks, not necessarily sequential ones, but more complex forms of social networks. And I forget about the epistemics part there for a moment, just to see like how are we modeling the structure of these networks. And then in part 3, and that will be later this afternoon, I'll study social influence in epistemic social networks. So these are networks where both the social ingredient or dimension and the epistemic dimension are going to be important. And I will look at the dynamics of the social relations. So the friendship dynamics is going to play a role, and that is for this afternoon. Okay, so that's what I'll do today. So we'll start, first of all, in the background of everything that I'll do will be epistemic models. And these are going to be social networks, so multi-agent epistemic models. They have a number of ingredients, so probably you've seen this before, but okay, so my setting and notation are important here. S is going to be a finite state space, or a set of states or possible worlds. My set of agents is going to be denoted by a set A. And for every agent, I'm going to add a relation over the state space. And these are labeled by the agents. So my little squiggly tilde is going to be an equivalence relation for every agent. And these equivalence relations for agents, they generate for every agent an information partition. So I say that 2 states S and T are related. Let's see if this thing works. Yeah, here. So they are related in this way. When S and T belong to the same information cell that this equivalence relation over the state space generates. And I have a standard valuation map, which assigns to the elements from a given set of atomic sentences, atomic propositions, the states, the set of states where that proposition is true. So this is the start. These are epistemic models. And then for this binary relation that I have, which was here an equivalence relation on the set of all states or possible worlds, I'm going to introduce an operator. And the operator is written by a box notation around a relation, which maps any proposition, and a proposition is a set of states, into another proposition, box P. Where box P for the relation R is just a set of states S, such that for every T that is related to it, proposition P is true. So this box P is called the Kripke modality for that relation R, right? So I have a Kripke model, and this is my first model operator that I introduce here, and this is then called the Kripke modality. Now, so in the epistemic models that I start with, my relation is an equivalence relation. And so the Kripke modality for that equivalence relation is the model operator for knowledge of an agent. So knowledge is a special case of operator, indeed, the one in which my equivalence relation in this case is going to be an My indistinguishability relation is an equivalence relation. I could take other relations, not equivalence relations, weaker ones. So, but for now, and on most of the talk, when I talk about knowledge, it is going to be a hard kind of knowledge. So the Kripke modality is for this relation that I started with. This type of operator is also studied in game theory. It boils down to the standard Ullmann definition in game theory. And what it captures is that something is known if and only if it is true within the same information cell as the real world for that agent A. All right, so that's how we know how we start with an epistemic model and the notion of knowledge for every agent. So these are very simple structures. Now, in addition, when I say I want to study belief formation and informational cascades, I need something else. So in addition to knowledge, I need to model the beliefs of an agent, the opinions or the beliefs. So I'm going to introduce, basically you would introduce a new Kripke modality, a new operator, but now for belief. Then you would ask me, okay, what should be the relation underlying that modality? What people have done, the logicians who've studied epistemic and stochastic logic, they either have added a whole series of new relations for each agent. Typically, these are weaker than equivalence relations, but they would say, for belief, you need a serial relation. So that would be a Kripke modality for a notion of belief that models belief directly. There is another way to do it, which is called, you could introduce what is called a plausibility relation. And what it would do is it takes an information cell of an agent, so the knowledge cell of the agent, and the plausibility relation will indicate which worlds or states the agent considers more plausible than another one. So you would have like a pre-order ranking over the states in the information cell. That would be one way in which you could do it. Another one would be take the information cell of the agent and you add a probability function. So in each agent's information cell, these functions, and you can treat them as accessibility relations, will indicate the worlds that an agent considers more probable. So there are different ways in which I can model beliefs. And what I'll do in this first part of the tutorial, I will focus on the third option. I'm going to start with my epistemic models, where I have an equivalence relation for every agent, which gives me an information partition. And in that information partition, I'm going to add a probability function for every agent to represent the subjective beliefs of the agent. Okay, so I'll do that for a concrete example. So I'll introduce this whole setting for a very specific example, and that's the example of an informational cascade, because that's a social phenomenon that I want to model. What are these informational cascades? Well, first I'll tell you what these are. So this means that I have a sequence of agents, the topology is aligned, so people are standing in a line, and they observe the decisions of their predecessors in the sequence. And somehow they decide individually to each follow their predecessor. This means that they might ignore their own private information. They just follow the actions and the behavior of their predecessor in the sequence. And I have here a picture of the ducks in Amsterdam. So the ducks in the canal here, you can see this type of behavior for the ducks, but the ducks are very different from people, because the ones that I want to model are not the people that just mindlessly imitate their predecessors. They have a rational choice. They have their own private information, and still in an informational cascade, they end up following their predecessor. Sometimes a cascade can be good, but sometimes cascades are bad. So here is an example and a picture of a cascade that you don't want to happen. So this is a court case, and the last one of the jury members says, well, heck, if you all smart cookies agree, who am I to dissent? So you don't want that to happen if you're the one on trial, right? So So we observe sequential deliberation protocols that can lead to epistemic failures where the group as a whole follows the predecessors, but they do not track the truth. So the whole group may deviate from the truth. Now, to model such situations, I'm going to start with a very concrete example that is easy to model, because the behavior of people in the real world is messy in the sense that there are many parameters, many variables. It's very complicated to really model it, but I'm going to look at a very concrete scenario where it's clear what the propositions are, where it's clear what the beliefs are, what the knowledge is. And so that's easier to model if you take a very concrete, well-defined scenario. Okay, so my example is going to be an EARN example. I have a series of agents, people, and I label them A1, 2, it goes on, AN. And they enter a room, so I've drawn the room here, where all these agents in a line, they all enter that room. And then in the room is an EARN, and it's either the EARN B or the EARN W, but none of the agents know which EARN is in the room. But what they do know about the EARN is that EARN B, the black EARN, B stands for black here, contains a majority of black balls. So 2 black balls and 1 white ball. And EARN W is the other option, has 2 white balls and 1 black ball. So they know that in that room is one of these 2 EARNs, they don't know which one. Now, what the agents can do one by one is when they enter the room, they can take a ball out of the EARN, they can look at it, sample one of the balls, look at the color and put it back. Okay, and they put it back, they go out of the room, and then they publicly announce a guess. They guess either the EARN in the room should be EARN B or should be EARN W. So that's the guess. And they announce their guess publicly for everybody else who comes after them to go into the room to hear. All right, so that's my setup. So let's see what happens. Suppose that the actual EARN in the room is EARN W, nobody knows that. And the first agent goes in, looks at a ball and sees that it's a black ball. And she knows that the black EARN has actually majority of black balls, 2 black balls, 1 white ball. So her guess rationally should be for the B1, B EARN, right? So that's all the information that the first agent has. She puts the ball back, then the second agent goes in. Suppose the second agent also takes a ball, looks at it, sees a black one. Then, now the question is, if she puts it back, the rational guess for the second agent should also be EARN B. She puts it back, she makes her announcement, and she goes out. Now the third agent goes in. And the question is, what will happen next? So now the third agent will look and take a look at the ball. So she has 1 item of private information, but she already has 2 items of other public information for 2 black balls. And that information will outweigh whatever color of ball that she sees, right? So if the third agent, suppose that she sees a white ball, then all the information that she has from the previous agents outweighs the information that she has. So the only rational choice for the third agent here is that she has to guess EARN B. However, and she announces her guess for EARN B. Now, the third guess actually is uninformative because the fourth agent, the fifth agents, everybody who follows after that has exactly the same information as the third agent. The fourth and the fifth, they all heard the first 2 guesses. They can deduce that the EARN must be B, that they guessed B on the basis of seeing a black ball. So this means there are 2 pieces of information for black balls for everybody who follows. So 1 million people, they all are going to vote for EARN B. So this means a cascade is formed here. And we assumed that the urn, the real one that was in the room, actually is the white one. So with a fixed probability of 1/9, when the first two agents all see a black ball, which can happen with probability 1/9, all the agents, 1 million people that follow, all get it wrong. Okay, so this is an example of an informational cascade, which is easy to model because we have the urns, we know what the pieces of private information is, we know what happens, what the announcements are, which events happen, and in this case, a cascade is formed. Now you can ask yourself a number of things. Typically, the analysis that is done in terms of Bayesian probability theory. And you can ask yourself, is this rational behavior? Well, so the Bayesian account would actually say, yes, this is all rational. Because given the available information that the agents have, if the agents are interested in individual truth tracking, then actually they should behave as above. They take all the information that they have available into account, they calculate the probabilities, and they should behave in this way that agent number 3, number 4, everybody votes for the black urn. Now, another question that you can ask yourself is, but can't these agents reason, right? So they reason about the beliefs of other agents, so they take higher order beliefs into account. And moreover, maybe if they realize that they're part of a cascade, can they not avoid being into a cascade? And what we can do is, well, in order to show this, it would be good to have logic where you can actually model the higher order reasoning of agents. And what we can show is that agents that are in this situation, when they can do higher order reasoning, they might be able to avoid some cascades, but not this one, not the one in the case of the urn. So
can I just ask, but wouldn't it for the third agent important to know whether they are either paid to get it right, so that they would do just what's the best probability for them, or whether they have an intention to get it overall in the long term, right, and that they would do act differently, because then they know it would be better to give the information I have.
Well, so you're right that if you do, I'll come to that point later on, that if you do a game theoretic analysis, you would assume that there is an incentive for them or a payoff for them to get it individually right, or what should be the decision if you want the majority of everybody, the whole group, to track the truth. So there will be a difference if the whole group is supposed to get it right, or if they individually have to get it right. In this case that I'm analyzing, it is as if they individually have to get it right. So they're individual, you can think of the scenario in which there are individual payoffs, and then they will behave in this way. But you're fully right that if the group behavior is the thing that we value more, then their behavior is supposed to be different. They can, of course, every individual agent could ignore the signals from the other ones, and that's a choice that they have. They can just ignore their predecessors as all and only announce on the basis of their own private signal that they get, which would be one rational way in which they could get out of that. But okay, so the scenario that I'm looking at is the one in which they individually have to get it right. But indeed, if I do a game theoretic analysis, make the payoffs clear, which one of our students did, then there are choices to be made. So in this scenario, I'm assuming that every individual agent wants to track the truth, and then the rational thing is indeed that they have to take all their information into account, and no amount of higher order reasoning is going to save them. And also, it doesn't matter if we're looking at 10 agents or at 2 million agents. Of course, in reality, the behavioral analysis in cognitive science will show that in reality, it will make a difference if the number of people that are actually in a cascade is bigger. So there are differences that could be observed, but that is really like a different type of study. So on the rationality account, when we only look at what is rational to do on the basis of reasoning and information that agents have, there should not be a difference in the size of the group. Okay, so how am I going to model this? I'm going to use dynamic epistemic logic to do so. And since the urn example has probabilistic information, so 2 black balls, 1/3 white balls in the black urn, I'm going to use a probabilistic extension of dynamic epistemic logic. And epistemic logic has the added value that it can model all the levels of mutual belief and knowledge about the current state of the world. So higher order reasoning is easy to model within an epistemic account. The dynamics add to this that actually now we can also model which events are happening, not just the state of the world, the possible worlds, but also we're going to model the protocol or the fact that somebody observes a ball or that they communicate their guess. All these actions can be modeled, and that is going to trigger a change in the epistemic state of the agents. And the logic that we have can actually help us compute this in an automated way. And given the examples are probabilistic, so I'm adding the probabilities to this. Okay, so the way that we are going to compute how a model or the epistemic change of agents happens is by using a model transformation action. And I'll illustrate how that works. So we're not looking at transitions within possible worlds, within one model, but we are changing one model to a next model. And in order to do that, I'm going to use a technique from dynamic epistemic logic, which is based on a product update method, which dates back to the work of Baltag, Moss, and Solersky. And I will have a reference later on. And the probabilistic extension of that type of logic is work that is done by other colleagues in the Netherlands, so Bartelt Kooi in Groningen, but together with Johan van Bentum and with Jelle Gerbrandy. Okay, so how do these probabilistic epistemic state models look like? So I already started with an epistemic model before, where I have a set of states. I have equivalence relations for each agent. So the little tildes give me the information partition for each agent. And now I add a probability measure to each equivalence class for each agent. So here, my notation P of A would be the probability measure for each agent. And I'm asking these to add up to 1 within the equivalence class for a given agent. And I still have a standard valuation map that assigns to each atomic sentence from a given set of atomic sentences the set of states where this proposition is true. So let's look at my urn example where I have 2 propositions. The urn in the room is the white one, and I add a star to indicate that this state is actually the real state, or the urn in the room is the black one, and all my agents' information partition is the one which I'm drawing here. Of course, that relation as a relation is also reflexive, and I'm not drawing the reflexive loops. So this is just a equivalence relation for all of the agents between those 2 options. And I've added the probabilistic info into the states. So everybody considers it equally probable that this urn W versus urn B, and these are all the agents that enter into the room. Now, there is another way, and maybe an easier way to write it down and to also draw it, is to represent the probabilistic information equivalently in terms of relative odds or relative likelihood between 2 indistinguishable states. So I can say that 2 states, S and T, and I write it like this to express the relative likelihood of state S over T. And how is that defined? Well, as the probability for the state S over the probability for the state T, right? This is for individual states, but I can generalize the notation to sets of states, which are propositions. So I can say that earn B, for instance, would be more likely than earn W. Or like arbitrary proposition E would be more likely than a proposition F. And this means that I take the probability that I assign to proposition E over the probability that I assign to proposition F. And these are just summing up the probabilities for the states that are contained within the proposition E. So if I have this, then it would be easier for me to draw now within an information cell. Now I can draw the relative likelihoods. So this means I'm going to draw from a state that has a lower odd to an arrow pointing to a state that has a higher odd. And when the odds are equal, 1 to 1, I might draw the arrow in both ways. So as before, I'm not going to draw the reflexive arrows. So the same situation now can be represented in terms of odds. So initially, the odds are 1 to 1. And I write the odds here for all of the agents. So all 1 million agents, AN, they have the same odds 1 to 1 for the urn being the white urn or to be the black urn. So that's an easier way to represent it. Now an event happens, right? So this is the initial situation before anybody has entered the room and nobody has yet looked at any ball. So now the first agent enters the room, she picks a black ball, she makes an announcement about her guest, and the second agent goes in, takes a ball, etc. So events start to happen. This means that I have to model the events, and I'm going to model, like in dynamic epistemic logic, the events differently from the way that I've modeled the states. So I'm introducing an event model. And this is going to be a probabilistic event model because the information that I'm encoding here is going to be probabilistic information. So it has a similar signature as the state model, so very similar to that one, but now I talk about events. So I'll use the notation sigma for the set of all possible events, and the little events are E, E prime, E double prime, so all kinds of events that can happen. Again, here I have a set of agents, and some agents might not know which events happen, but they think 2 events are equally possibly the case. So an equivalence relation indicates the hard information that an agent has about which events are taking place. So I have this equivalence relation now over events. Again, within that equivalence relation, that gives me an information cell for an agent, I can assign a subjective probability measure for the agent's subjective information that she has about which event is more likely to be the case. I can express this probabilistic information, the subjective probabilities for the agent over the information cell in terms of probabilistic odds. So I can say event E is relatively more likely versus event E prime for agent A. Now, in addition, when I talk about events, I might write a sentence that needs to be true for an event to happen, and these are called preconditions. So I'm given this family of sentences, and that's called pre. And that family of sentences determines the circumstances or the propositions that need to be true for an event to happen. Now, of course, in this case, when an event can occur or not is probabilistically determined. Like I can only see a black ball or I can see a white ball depending on what the distribution of the balls are in the urns that I'm looking at. So I add an occurrence probability and I write it as mu. So mu is a conditional mass function here that assigns to each event and each formula precondition a number. And that represents the prior conditional probability that that event can actually occur in a state that satisfies this precondition phi. This I will see an example how this works. So the conditional mass function here is required to satisfy that for every event, there should always be one formula such that this number is not going to be zero. So I always have events that can happen, are included in the setting. And I want this to add up. So for every formula of my preconditions that if I look at the events, then the sum of this has to add up to 1. So let's look now at, so here the occurrence probability is assigned to formulas, preconditions, but I can also define it in terms of states directly. I can compute when an event can happen in a given state. So that is information in a state S coming from my epistemic model. And the way that I would do that is that I write mu E given S. That should be possible to be given by mu E of phi, when phi is one of the formulas in my precondition for that event, and should be 0 if no such precondition is the case. So here I capture the prior occurrence probability that a given event E can happen in a given state S. Right, so now let's look at my example, how that works. So an event happens. The first agent goes in and she sees a black ball. Well, there are 2 possible events that can happen. Either she sees a white ball or she sees a black ball, right? So the event that can possibly happen, I write it with small w and small b for the event that occurs. And I write it below this line here. So 2 possible events. Now, agent 1 who goes in and sees the color of the ball, she can distinguish whether she sees a black ball or a white ball. So there's no uncertainty for agent 1. But all the others don't know what she sees. So all the others will have indistinguishability relations between these 2 possible events that happen. Now, the occurrence probability of when she can see a black ball is the thing that I've written above the line. So here I've written that this can happen when the real urn in the room would be the white one. She can see a black ball with a probability of 1/3. And if the real urn in the room is the black one, then she can see this. It can happen with the probability of 2/3. If she would see a white ball, then this can happen with the real urn W, 2/3. And if the real urn is the black one, then the chances for her to see a white ball would be 1/3. Okay, so this gives me the event model. And here, so you see there are 2 types of probabilistic information that I'm representing here. One is the subjective probabilities for all of the agents expressed in terms of relative odds. And the other is when an event can occur. This is the occurrence probabilities, which I write in the events. All right, so that's what happens when a first agent goes in. We draw this as an event model in this way. Now I have an original state model where nobody knows which urn is in the room. The odds are 1-to-1. And I have the event model for the first agent picking a black ball. So what do I do next is that I have 2 models of a similar type of signature. And I'm going to compute how to represent what happens to the state model given this event that happened. I do that by updating. I take the product of my event model and I write event model as E with my state model N. I take the product and I compute what should be the new states, what is the new information cell for every agent, what are the new probabilities, and I do that in an automated way. How? Well, I have to tell you. So how do I compute the new state model? The new state space is going to be, well, the Cartesian product of the states from my original model with all the events. I take the Cartesian product, which will be a bigger model indeed. But of course, not all events match with all states, only the ones in which the occurrence probability is not 0. right? So I put a condition that the occurrence probability should not be 0. What are the new epistemic relations in my new model? And note that now I'm going to represent the pairs in my updated model are pairs of states with events. And I might also write them as just SE, concatenated. So I don't really write the tuples out completely. So two new states in my updated model are going to be related epistemically for an agent A. When? Well, when she cannot distinguish the two states and she cannot distinguish the two events. So when both these, the equivalence holds, the indistinguishability holds between S and T and between the events E and F. And what is the new subjective probability that she has to assign? I give it again in terms of the relative likelihoods. Well, that's easy. I take the probability that she assigns given her equivalence class in the state model, and I multiply it with the probability over the events, and I take into account when these events can occur. I take the occurrence probabilities into account. So I just multiply the probabilities together, taking the occurrence into account, and that gives me a new updated state model. And of course, you could say, well, for this simple example, indeed, you can also draw it by hand. You don't need a whole automated way to compute the updates every time. But I can assure you that there are lots of examples in scenarios that we can come up with when the initial states are maybe more complex, when there's much more lack of knowledge and different private information that the agents have, when this method is going to be very useful. Okay, so let's do the computation now. I have an initial model. The odds are 1-to-1 that the earnest W versus B before anybody entered the room. The first agent takes a black ball. So she knows this is the real event. The others don't know whether W or B happened. And now I compute the update. So I have two elements of my state space for the state model, and I have two events. So the Cartesian product gives me 4 ingredients for my updated state space. All right, so I combine this with this, and this with this, and this with this, and this with this. So, and I take the occurrence probabilities into account. So when can this happen? So the updated model will have 4 states. Either the urn in the room is W and she sees a white ball, the first agent, or it's a black urn and she sees a white ball, or it's a white urn, she sees a black ball, and it's the black urn and she sees a black ball. Now, the agent 1, who went into the room and did the event, she saw a black ball, she knows that she's in this part of the model. Either it's W or B, and she saw a black ball. Right? So that's what this information encodes. So she knows she's in this part of the model, and the top part is not possible for her. But the others don't know. They cannot distinguish that. So for them, they take all possible 4 states into account, of course, with different probabilities, because the relative odds, how are the relative odds here computed? Well, when the urn is W and you see a black ball, or the urn is B and you see a black ball, so this has a higher relative likelihood than that one, right? So it's 2-to-1 that this would be the real case. If agent 1 would have seen a white ball, then it would be much more likely that the real urn is the white one. So the relative odds here, if this would be the scenario, would be 2-to-1. Okay, so now, the next thing that happens, I said that when agents see the color of a ball, they publicly announce it. So a guess is announced. That's a public announcement, which is, again, an event. So there is an event model for a public announcement. The formula that is announced, I've written that formula as, well, she sees a black ball, so her announcement is that the relative likelihood for B is more likely than W. And I write it as B to W should be bigger than 1. It just encodes this information. So this is a linguistic construct in the language that encodes the fact that the probability she assigns to the urn B is higher than the probability that she assigns to the urn W. It's an event model which has the occurrence probability, and the occurrence probability will be as follows. So the fact that she announces that, sorry, that should be, so I've switched that here. So she announces that B is more likely than W, and the occurrence probability for that is that she cannot announce that in case she saw a white ball. So the occurrence probability for this event to take place is 0 in the case that she announces a white ball. But it is 1 in case that she announces that she makes this announcement in case that she saw a black ball. So given this event and this being the state, that should be 1. Now, given that announcement, and that's a public announcement, we look at the model that we had. The proposition is going to be true in this part, in the lower part of the model, namely that B is more likely than W. It is not true in the upper part of the model. So what happens is that all the agents now get the information that they delete the upper part of the model. The model shrinks to this one. So first agent sees a black ball and B is more likely than W, 2 to 1. Okay, so now we continue. The second agent goes into the room, sees a black ball, makes an announcement, says that her guess is B is more likely than W. Again, we compute the update product. The model is going to increase. The announcement is going to throw away part of the model. And what we end up with is this one. So either earn W is the real one and the first two agents see a black ball, or the earn is the black one and the first two agents see a black ball. Now the odds, since we multiply, the numbers get higher. So the odds are 4 to 1 that this is the case versus that is the case. Now the cascade is triggered when agent 3 enters. Agent 3 enters and she sees a white ball. So again, we have an event model with these two possible events. Either she sees a white ball or a black ball. Nobody can distinguish it, but agent 3 knows. So there is no indistinguishability for agent 3. And the real event is going to be the white one. She makes an announcement, but now it's interesting to see what happens to the model. So we compute what happens to the model. And we see that the update of the model is going to be such that no matter which color of the ball that she saw, in all cases, all arrows will point to the black urn. So when we are here and the real urn would be the white one, or would be considered to be white, all agents will think it is more likely 8 to 1 that the black urn is the real one. Or when we are here, all arrows point to this case, when the black urn is the real urn. So when the third agent makes an announcement that the black urn is more likely than the white urn, the model is no longer going to shrink, because that is true in all parts of the model. So irrespectively of what information that private information the third agent got, and whatever announcement that she makes, based on the information that she got from the first two agents, she will announce that B is more likely than W. The model is not going to shrink anymore. Moreover, here you can see that given the odds that we have in the model, everybody is going to guess for B. So this indicates that from now on, the cascade is formed. So the situation repeats itself, all agents, and we can compute the next update and the next update. So you can automatically compute all these updates. All agents from now on will consider earn B to be more probable than earn W in all states. Right, so that's a specific way in which we're modeling using these computations in dynamic epistemic logic to model the formation of these cascades. And we wanted to do that specifically because making the epistemic information explicit allows to take into account the higher order reasoning of these rational agents. And we see that it is still rational for them to follow the cascade. So we've written this up in this paper, in which we provided the full probabilistic account that I just presented. But in addition, we also added a qualitative account where agents would simply be counting pieces of evidence, because people have thought that, well, you don't need full probability theory, you can just count how many pieces of evidence an agent has in favor of one of the two errors. And indeed, you could simply also model that, not in a probabilistic way, but using a qualitative logic in which you make the evidence, the private and public evidence that agents have available. So that we did in this paper. There is, what I didn't do here is a proof theoretic full syntactic encoding of what happens. I've shown you the mechanism based on the models. There is a paper by Alexandra's student, former student, Andrea Archimescu, together with one of our former postdocs, Joshua Sack, in which they made the whole logical argument within the language of, they use a variation of epistemic probabilistic dynamic, no, PDL, epistemic PDL, fully clear. Now, related to the question that we earlier got, indeed, you can also provide a full game theoretic account of this, and that's what one of our master students did in her thesis. Because the behavior that I've modeled here is the behavior when each agent is rewarded for her individual performance. If you ask the group, if you change the payoffs and you say that, well, the majority of the group has to track the truth, everybody has to take it into account, then indeed the cascade will not form. Rational players, if they are fully rational, would have to disregard the information received from others. And that would take into account the advantages of the Condorcet-Jury theorem, for those who are familiar with that. There's much more to say on the game theoretic account, but that's actually what I wanted to show on the modeling of the informational cascades. Now, the next thing that I want to do is to start already with the second part of the tutorial, where I'm going to make the social network explicit. So till now, the whole social structure was left implicit. I was starting from epistemic models, and the network structure could be deduced from the order of the events. First, one ball was drawn, this is an event, and then an announcement is made. So there was a sequential order of events from which you can deduce the topological structure of the network. But when you really want to model the social networks, then it would be important to make the social network structure into account. Leaving the epistemic, for now, I'm going to leave the epistemic part on the background, focus on the social part. This means I start with, yeah, and then 5, and then questions, right? Yes, okay. So I start with a network of agents, which is an undirected graph. And all these agents now have a behavior. They might have they have a like, they adopt a fashion. So I have atomic sentences that I distribute over all the agents in the network. I can even say that they believe or disbelieve a proposition, but belief here is just going to be an atomic sentence. Not yet any fancy structure for the beliefs as I had previously with the probabilistic subjective probabilities. Now, what is crucial is that such a network where I just have agents and atomic sentences distributed over them can change in 2 possible ways. Either I'm going to change the social structure, delete agents, add new agents, change who's related to who, which I'll do later on. Or I'm going to change their behavior. Say like, well, they're going to be influenced by their friends and they get new information from their friends, and whatever proposition P is true for one agent is going to change in the next round after they've been influenced. So in this case, I'm going to restrict it to agents that get only information from their friends. So not from the outside walls, no urns where they are drawing balls. So all the information that they get is from their friends. So it's a very specific type of social situation that I'm looking at. So agents being influenced by their friends, and what can happen is that they change their belief or their fashion. They adopted fashion P and they might change it to fashion not P. And when this can happen depends on a certain threshold. The threshold I'm going to denote as theta. And theta denotes the fraction of her friends, the threshold that is a fixed percentage that helps you model when an agent is going to adopt a new fashion. So how do the thresholds model look like for social networks? These are also very simple models. So now I don't have possible walls or states, but I have agents. My nodes in the network now are agents. I have a binary relation over the set of agents, and I denote it by F, and F is my friendship relation. Have a set of atomic sentences, PQs, that are distributed over the network in the sense that agents have a certain property P or they don't have a certain property P. And as I said, there is then a dynamic rule that indicates when an agent changes her fashion or adopts a new proposition. It of course depends on what is the what are the properties of the social relation here. When I'm really modeling friendship, you want that relation to be irreflexive and symmetric, assuming that friendship typically is mutual. But I'm not necessarily going to assume that in the talk. So I will also allow for the case where I model a notion of informational access, where I can access my own Facebook account or my own posts on a blog. So an agent can access somebody. So AFB would then mean that A can access B's informational database, and AFA would certainly make sense that A can access her own database. I'm using the notation F of A to denote the set of all agents' friends, everybody who's related to her. Then when an agent changes a property that she has, a fashion that she has, we need an adoption rule. I need a rule to specify exactly when this happens. And that deed is given a certain threshold theta. Now the threshold can be an absolute number, or it can be percentage of somebody's friends, so that I can model the situations such as that if at least 100 of my friends like Lady Gaga, then I start liking her too. Or everybody watched football last night on TV, so I should have watched it too. Or if at least 2/3 of my friends join an online discussion group, then I join. It can be part of my friends, but you could also say, well, no, maybe I should look at all agents in the population. So there are different choices that you can make on what the threshold should be. Now, yeah, maybe before I can do the generalization of these type of networks after lunch. And what I want to do here is to look again at the formation of cascades in these networks that are not necessarily sequential. And then later on, the last part of the presentation will be about changing the friendship relation. So changing the social structure. Okay, so let me conclude this part of the tutorial for now here.
Thank you very much. As before, we're switching minds. Because this one is more. Questions?
It's a very interesting approach. But I mean, the first part, it seems somewhat pessimistic. Depending on your goal, either you want to be personally not getting rewarded, then you totally fall for social evidence, or you want to be social, then you disregard social evidence for the totally. I mean, those doesn't seem to be very rational. I mean, if 1,000 people before me independently saw a black bird or black armor or so, then probably it's rational for me actually to disregard my evidence. So did you look into any kind of mixed strategies? I mean, there must be some way to make sense of other people's evidence show, right?
Well, I mean, it really depends on the notion of rationality and the type of structure or the strategy that the agents have. So if you, so what you're asking really is more on the making all that explicit. So you have to then say, well, what is the individual strategy of an agent? Does she individually want to get it right? Does she want to get it right as a group? Or is there a mixture of those? And that there are ways in which you can model that, but then you really have to model the type of strategies and the type, you have to really take into account who can communicate to whom and which information that is being communicated are you taking into account and which are you not taking into account. There are certain types of networks or games, let's say, that are equivalent to the Condorcet type of thing where everybody converges to the truth, which is the one that society typically is more interested in. But what triggered me in looking also just at the logic part for this is the discrepancy between the amount of communication that happens. So suppose no communication happens, nobody announces any of their guesses. Then it's the same as if agents ignore the information from the others and the whole group gets it right. So when you allow zero communication, in this case, the group tracks the truth. When you allow some communication, suddenly, if they then individually track the truth, then suddenly a little bit of communication gets everybody astray. If you again allow all communication, namely not only the guesses of the urns that agents are interested in, but allow the agents to communicate the information that they saw, the private information that they saw. So agent 3 is going to say, I took this is my guess, but in addition, it is based on the fact that I saw a white ball and the others. So then you see the frequency of what the occurrence really is. Then, of course, full communication, everybody gets it right again. So what I'm interested in was also that zero communication, everybody gets it right. A bit of communication, as in this situation, they announce their guesses, but not their private information. They get it wrong. Full communication, they get it right again. So I'm also intrigued by this amount of information and communication that is going on. And indeed, I mean, it is pessimistic, but in a way, yeah, it's still individual rational behavior, but it depends on the notion of rationality.
Maybe I can follow up on this as the chair with the question. So there is some component of time. This is hard coded in the structure because they are doing this in sequence. In practical situations where we are normally not lined up in a sequence, there's also a decision about when to speak up. I think Johan van Benten has talked about this in the past, that you need to find the right moment so that your information is crucial for the further development. And we've all seen skates in committees. The skates usually happen by someone speaking up in the right moment, usually one other person seconding that opinion and saying, I agree, and then silence. And that silence is the cascade. And this is silent agreement to what has been said, which comes, so what is happening there, and this is why it's related to Merlin's question, is that the more people have agreed to this, the higher the cost of speaking up and disagreeing. That fits with the jury. And so there are lots of people who have already said, my social cost of speaking up and saying, actually, I disagree with that, becomes higher and higher. So are there any attempts to build this into the game theoretic network, the social cost of speaking, and also the choosing the right moment?
Well, not in these logic settings that I know of, but of course, in behavioral economics and the link to cognitive science. There is a huge amount of literature on the formation of cascades and what happens. And there is, of course, social choice theory, which also relates to deliberation in juries, etc. So it might very well be that when you actually model a deliberation scenario, that people have looked into taking the costs into account of that to speak. Here, there is no time in this network, for sure. There are other types of ways of modeling epistemic scenarios when time is relevant and where I can actually take into account when an agent makes a certain announcement. Related to the talk of Roman that we saw yesterday, actually there is a whole framework that is in some senses, some parts are equivalent to the way that dynamic epistemic logic models it. The runs and interpreted systems of Joe Halpern, Bartley, and Moses. They have a way in which the information of the agents, epistemic information, changes over time, and in their model, the time is really modeled explicitly. Yeah, so then a moment of silence could be built in. I mean, we can do that here as well, right? So there is a moment of silence that you could build in, but it would be actions in which not really, yeah, you would have to model it in a certain way because you don't want to say the action isn't happening. There is a tick of the time clock that is happening. So it should be possible to model that here as well, but it might be less elegant than in a model where you have time explicitly. Yeah, no, that could be done. It could be interesting to actually see what happens and to take the costs into account of like previous agents speaking, what that actually means for triggering the cascade and when actually the cascade is formed. Yeah, that's an interesting suggestion.
So we're looking forward to a second part of the tutorial, which is at what time? 2:30. 2:30. So everyone.
No,
1:30. Yes. Oh yeah, the lunch is very. The timing of the lunch is very dodgy. Maybe you want to make the announcement?